Cambridge, England, April 2025. The Institute of Astronomy at the University of Cambridge, the office of Nikku Madhusudhan, professor of astrophysics and astrochemistry. He has been working on this paper for months. His team has been awarded observing time on the James Webb Space Telescope using the MIRI instrument, the mid-infrared instrument, which extends JWST spectral coverage further into the infrared than the near-infrared instruments used in the team's previous observations in 2023. The target is K2-18b, a planet orbiting a dim red star about 124 light-years away, a planet they have been studying for 2 years. A planet whose atmosphere, in their previous observations, had already produced a result that made headlines around the world. He opens the new data on his screen, the transmission spectrum of K2-18b, the plot of how much extra starlight is absorbed at each wavelength as the planet passes in front of its star, appears. 2 features are familiar. They have seen them before: methane, carbon dioxide, the same molecules detected in 2023, now being probed in the mid-infrared as well. He looks further along the spectrum. There is a third feature. It sits in the mid-infrared range, between roughly 5 and 12 microns, at wavelengths that his atmospheric models had flagged in advance as potentially diagnostic of a specific class of molecule, dimethyl sulfide, DMS. On Earth, DMS is produced overwhelmingly by one thing: marine life, phytoplankton, algae, microorganisms in the ocean. It is part of what gives the sea its characteristic smell. It plays a role in cloud formation over the ocean, providing nucleation sites for water droplets. It is, on our planet, considered one of the clearer chemical markers of biological activity. That distinctive sea smell you notice at the coast, the one we tend to associate with salt water and ocean air, is in significant part the smell of DMS, released by countless microscopic organisms living in the surface waters. It is, in a real sense, the smell of an ocean full of life, which is exactly why a feature in the spectrum of a distant world at the wavelengths where DMS absorbs would stop an astronomer cold. On Earth, that molecule means life. The question the entire rest of this story turns on is whether it must mean the same thing on a world utterly unlike our own. And a feature consistent with it appears to be in the atmosphere of a planet orbiting a star 124 light-years from Earth. Madhusudhan runs the atmospheric retrieval. The DMS feature comes out at around 3 sigma confidence, statistically meaningful, not definitive, but not nothing. Something is there at those wavelengths, and one of the best fits to the data involves dimethyl sulfide, or its close relative dimethyl disulfide, DMDS. He looks at the screen for a long time. Then, he calls a meeting of his team. The paper they will write is careful, it is hedged, caveats are included, alternative interpretations are acknowledged. Madhusudhan has spent his career studying exoplanet atmospheres, and he knows how easily a marginal signal can be misinterpreted. The paper is published on April 16, 2025, accepted in the Astrophysical Journal Letters. The Cambridge press release goes out around the same time. The framing, the strongest signs yet of a possible biosignature on an exoplanet. By the end of the day, it is everywhere: CNN, BBC, The New York Times, every major news outlet on Earth reporting that scientists may have found signs of life on a distant planet. For a brief moment in April 2025, much of the world believed that the James Webb Space Telescope had found what humanity has been searching for since we first understood what the stars were. The reality, when the scientific community had a chance to look carefully at the data, was more complicated, more interesting, and more honest than the headline. Madhusudhan and his team were not wrong to publish. The signal was real, in the sense that something was producing a feature in that part of the spectrum. The detection was statistically meaningful at the level they reported. The molecule they pointed to is, on Earth, a product of life, and the paper itself, carefully worded, heavily caveated, was a legitimate piece of science. And yet, within weeks, multiple independent teams had shown that the same data was consistent with explanations that required no life at all. Abiotic chemistry, photochemical reactions in a hydrogen-rich atmosphere. Molecules other than DMS fitting the spectral feature at comparable statistical significance. The most exciting candidate result in the history of the search for extraterrestrial life turned out to be exactly what the most careful scientists always said it would need to be tested against before it could be called a discovery. Not sufficient, not yet, and what the field learned from that insufficient result is changing the search permanently. This video is about K2-18b. It is about a planet about 124 light-years away, roughly 6 times Earth's mass, orbiting in the habitable zone of a red dwarf star, whose atmosphere JWST has been studying since 2023. About the carbon-based molecules that were detected in its atmosphere in that first round of observations. About the DMS signal that appeared in the April 2025 follow-up and triggered one of the most intense scientific debates in exoplanet astronomy in years. And it is about what the debate revealed. Not about whether K2-18b hosts life, that question remains genuinely open, but about the specific state of the science of biosignature detection. About what it actually takes to confirm that a molecule in a distant atmosphere came from life rather than from chemistry. About the gap between finding something interesting and proving it is what you hope it is. The K2-18b story may be the most important case study so far in the history of biosignature science. Not because life was found, because the search for life at K2-18b forced the entire field to confront, in concrete terms rather than theoretical ones, the specific limitations of current biosignature methodology, and to build, from those confrontations, a clearer understanding of what the next generation of observations needs to do. By the end of this video, you will understand exactly what JWST found on K2-18b. You will understand why it was genuinely exciting, why it was contested, and what the scientific debate has revealed about what biosignature confirmation actually requires. And you will understand why the K2-18b story, whatever its final resolution, has changed the search for life beyond Earth. So what exactly did JWST find on K2-18b, and what did it not find? Why was the April 2025 announcement met with both genuine excitement and significant skepticism within the scientific community? What does DMS actually tell us about a planet's potential for life? And why might it mean something very different in K2-18b's specific atmospheric context than it would on Earth? What is a Hycean world, and is K2-18b really one? What does it take to confirm a biosignature, not just detect a signal, but show that the signal requires life to explain it? And why is that standard so difficult to meet? And what will JWST need to find in future observations of K2-18b or other nearby worlds to move the needle from a possible sign of life to something that scientists are willing to call genuine evidence? This is not a video announcing the discovery of alien life. JWST has not confirmed life on K2-18b. The scientific consensus, as of 2026, is that the DMS signal is statistically marginal, contested across multiple independent analyses, and cannot be uniquely attributed to biological activity in K2-18b's specific atmospheric context. Multiple leading exoplanet scientists have publicly stated that the enthusiasm in the April 2025 headlines exceeded the strength of the evidence. A paper from later in 2025, summarizing the community response, carries a title that says it plainly. K2-18b does not meet the standards of evidence for life. But this is also not a video dismissing what happened as a false alarm or a non-event. The methane and carbon dioxide detected in K2-18b's atmosphere in 2023 represent one of the first detections of carbon-based molecules in a habitable zone exoplanet atmosphere in the history of astronomy. That is a genuine landmark, regardless of what DMS does or does not turn out to mean. And the intense scientific activity that the April 2025 announcement triggered, the independent reanalyses, the photochemical modeling, the development of new biosignature validation frameworks, has advanced the field in ways that matter enormously for the search going forward. The honest version of this story is more interesting than either the discovery confirmed version or the nothing to see here version. Stay with me before we go deeper. If these are the kinds of stories that pull you in, the frontier of the search for life beyond Earth told carefully and honestly, hit subscribe. Galaxy Pulse goes beyond the headlines every single time. We will not tell you we found aliens when the science says it is not confirmed, but we will tell you what we actually found, why it matters, and why the question being asked is among the most important in the history of science. Now, back to K2-18b. To understand why the K2-18b story is so important, and why the scientific debate around it matters as much as the detection itself, we need to start from the beginning. What is K2-18b, and how did JWST detect anything in its atmosphere from over 100 light-years away? What is DMS, and why is it considered a biosignature on Earth? And what is the specific standard of evidence that the exoplanet science community requires before calling a signal a genuine sign of life? A standard that, as of today, the K2-18b data has not yet met. All of these questions start in the same place. With how we study planets we cannot visit. To study the atmosphere of a planet over 100 light-years away without being able to travel there requires a technique that is, when you think about it carefully, extraordinary. The technique is called transmission spectroscopy. When an exoplanet passes in front of its host star, a transit, the planet blocks a small fraction of the star's light, causing a temporary dimming that we can detect from Earth. This transit method is how K2-18b was discovered in the first place, by the Kepler Space Telescope's extended K2 mission in 2015. But the transit does more than simply block light. A tiny fraction of the starlight passes not through empty space, but through the thin outermost layers of the planet's atmosphere on its way to us. To appreciate how delicate this is, picture the geometry. The planet is a small dark disk crossing the face of a vastly larger, brilliant star. Almost all of the starlight we receive during the transit comes from the parts of the star the planet is not covering. Only a sliver of light grazes the very edge of the planet, passing through the thin ring of atmosphere around its limb before continuing toward Earth. It is that sliver, and only that sliver, that carries the chemical fingerprint of the atmosphere. Everything else is, for this purpose, glare. The astronomer's task is to isolate the chemical signature carried by that thin ring of light from the overwhelming brightness of the rest of the star, and to do it for a planet so far away that the entire system appears as a single unresolved point of light, even to the most powerful telescope ever built. Different molecules in the atmosphere absorb different wavelengths of light. Methane absorbs at certain wavelengths. Carbon dioxide has prominent features at others. Water vapor absorbs across a range of near-infrared wavelengths. DMS, and its relatives absorb in the mid-infrared. By comparing the spectrum of the star's light during a transit, when some of that light has passed through the planet's atmosphere, to the spectrum outside of transit, astronomers can identify which wavelengths are slightly more absorbed. Those wavelengths correspond to molecules present in the atmosphere. Each molecule, in effect, has its own barcode, a specific pattern of wavelengths at which it absorbs, determined by the quantum structure of the molecule and unchanging anywhere in the universe. The methane barcode is the same on K2-18b as it is in a laboratory on Earth. So, when astronomers see absorption at exactly the wavelengths methane should absorb, in the right proportions, they can be confident methane is there. The trouble, as we will see, is that some molecules have barcodes that overlap, that share many of the same lines, and when the data is noisy, telling one from another becomes genuinely difficult. This is the principle. The practice, at the sensitivity required to study K2-18b, is extraordinarily challenging. The signal being measured is a tiny fraction of the total starlight, on the order of 1 part in many tens of thousands. To detect the atmospheric absorption features of a trace molecule at the concentration levels relevant for something like DMS, you need a telescope with a combination of mirror size, wavelength coverage, and instrumental stability that, before JWST, simply did not exist. Consider the chain of difficulties stacked on top of one another. The planet's atmosphere imprints its signature on only a sliver of the starlight. That signature is faint to begin with. The star itself is not perfectly steady. Red dwarfs like K2-18 are prone to flares and starspots that can introduce their own variations into the light, variations that can mimic or mask an atmospheric signal. The instrument has its own quirks and drifts that must be modeled and removed, and the whole measurement must be repeated across multiple transits, each 1 hour long, with the results combined in a way that preserves the faint true signal while averaging away the noise. Every one of these steps is a place where error can creep in, and every one of them involves choices that different research teams may make differently. The remarkable thing is not that the teams sometimes disagree about K2-18b. The remarkable thing is that the measurement can be attempted at all. JWST primary mirror is about 6.5 meters across. Its wavelength range extends well into the mid-infrared. Its instruments are cooled to extremely low temperatures to minimize their own infrared emission, which would otherwise swamp the faint signals being measured. It is, by a wide margin, the most capable telescope ever built for this kind of work. To grasp why JWST in particular made this possible, consider what its predecessors could and could not do. The Hubble Space Telescope, for all its achievements, has a smaller mirror and a wavelength range that does not extend deep into the infrared, where many key molecular fingerprints lie. Ground-based telescopes, however large, must look through Earth's own atmosphere, which absorbs and distorts exactly the infrared light that carries the molecular signatures of interest, and which is itself full of the same molecules, water, carbon dioxide, methane, that astronomers are trying to detect on other worlds. JWST sidesteps both problems. It sits far from Earth, beyond the Moon's orbit, in the cold and dark, where its infrared detectors can work without interference. Its mirror is large enough to gather the faint light required, and its instruments are stable enough to measure changes in starlight at the level of a tiny fraction of a percent, repeatedly, across many hours of observation. No previous instrument combined all of these capabilities. The K2-18b measurements were, quite literally, not possible before JWST existed. When JWST began science operations, K2-18b was among the high-priority targets for its exoplanet atmospheric science program. The reason was simple. K2-18b, orbits in the habitable zone. It had been theoretically identified as a candidate Hycean world. If any exoplanet was going to show us something interesting about the chemistry of potentially life-bearing atmospheres, K2-18b was a strong candidate. Here is what K2-18b actually is, or what we think it is. K2-18b is a sub-Neptune, larger than Earth, smaller than Neptune. Its radius is roughly 2.6 times Earth's, and its mass is around 8.6 times Earth's. It orbits the red dwarf star K2-18 at a distance of about 0.14 astronomical units, roughly 20 times closer than Earth orbits the Sun. But because K2-18 is so much dimmer and cooler than our Sun, the equilibrium temperature at K2-18b's orbit lands in a range where, under the right atmospheric conditions, water could be liquid. The Hycean world concept, developed by Madhu Sudhin and colleagues in a theoretical paper in 2021, proposes a class of planets in this mass and temperature range that could maintain a liquid water ocean beneath a thick hydrogen-helium atmosphere. And in this model, the ocean's surface conditions are set largely by the weight of the overlying atmosphere. The conditions in such an ocean could, in principle, support life similar to Earth's marine microorganisms. The word Hycean itself is a blend of hydrogen and ocean. The idea is worth dwelling on, because it represents a genuine expansion of where we think life might be possible. For most of the history of the search for habitable worlds, the template was Earth, a rocky planet with a thin atmosphere, liquid water on its surface, orbiting a sun-like star at just the right distance. The habitable zone was defined narrowly around that template. The Hycean concept widens the template considerably. It says that a planet need not look like Earth to host an ocean. A larger world, wrapped in a thick hydrogen atmosphere, could maintain liquid water across a much broader range of orbital distances than a bare rocky planet could, because the thick atmosphere insulates and pressurizes the surface. If the concept is correct, the number of potentially habitable worlds in the galaxy could be far larger than the Earth template estimate suggests. And crucially, Hycean worlds around red dwarfs are easier to study with transit spectroscopy than Earth-like planets around Sun-like stars, because they are larger relative to their stars and transit more often. That combination, potentially habitable and relatively observable, is exactly why K2-18b became such a high-priority target. There is a tension built into the concept, though, and it sits at the heart of the K2-18b debate. The very thickness of the hydrogen atmosphere that makes a Hycean world potentially habitable also makes its surface conditions hard to determine from the outside. Depending on the exact mass of the atmosphere, the surface beneath it could be a temperate ocean, or it could be water under such enormous pressure and heat that it bears little resemblance to anything we would call habitable. From transit spectroscopy alone, distinguishing these cases is extremely difficult. The Hycean model is a real, physically motivated possibility. It is not the only possibility. This is the theoretical framework that Madhu Sudhin's team was testing with JWST. In 2023, they published their first results. Using JWST near-infrared instruments, they reported the detection of methane and carbon dioxide in K2-18b's atmosphere. This was, by itself, a landmark result. Carbon-based molecules had not previously been detected so clearly in the atmosphere of a habitable-zone exoplanet. The methane detection in particular was strong. They also reported a tentative, low-significance signal that might be consistent with DMS. Below the threshold for a confident detection claim, the methane and carbon dioxide were celebrated. The tentative DMS hint was noted with interest and appropriate caution. 2 years later, they returned to K2-18b with new data. This time, using JWST MIRI instrument, they extended their spectral coverage into the mid-infrared, a wavelength range where DMS and its relative DMDS have absorption features, and a feature consistent with DMS and or DMDS appeared, this time at around 3 sigma confidence. That is the moment this story really begins. Under standard expectations for a sub-Neptune atmosphere at K2-18b's temperature, here is what the models had predicted JWST might find. Hydrogen and helium, expected to dominate. Methane, a stable molecule in the reducing chemistry of a hydrogen-rich atmosphere. Carbon dioxide, which can form through various pathways, possibly water vapor. These were the expected constituents, the molecules that atmospheric chemistry models said should be there given K2-18b's temperature, pressure, and composition. What the models did not predict with any confidence was DMS. Dimethyl sulfide, chemical formula C2H6S, is a sulfur-bearing organic molecule. It has a strong, distinctive smell, often described as resembling the sea, or in higher concentrations, cooked cabbage. On Earth, it is produced overwhelmingly by marine phytoplankton and other microorganisms as a metabolic byproduct, released into the atmosphere where it plays roles in cloud formation and the sulfur cycle. In Earth's oxygen-rich atmosphere, there is no significant known non-biological pathway that produces DMS in detectable quantities. It is worth understanding why DMS became a target of interest for astrobiologists in the first place. The appeal of DMS as a biosignature is precisely its tight link to life on Earth. Oxygen, the most famous biosignature, can in principle be produced by some non-biological processes, which complicates its interpretation. DMS, by contrast, has on Earth essentially a single source: living organisms in the ocean. That apparent specificity made it attractive. A molecule that, if found in another atmosphere, might point more cleanly to life than oxygen does. This is exactly why Madhusudhan's team had flagged the relevant wavelengths in advance, and why the appearance of a feature there was so electrifying. The catch, and it is the catch that the entire subsequent controversy turns on, is that DMS's clean link to life is established only for Earth's oxygen-rich chemistry. Whether that link holds in a hydrogen-rich atmosphere around a red dwarf is a completely separate question, and one that had not been carefully answered before K2-18b made it urgent. If DMS were present in K2-18b's atmosphere at the concentrations the Madhusudhan team's analysis suggested, far higher than DMS levels in Earth's atmosphere, then on Earth, the only known explanation would be life. That is why the April 2025 paper produced the headlines it produced. That is why, for one news cycle, the world felt like it was on the edge of one of the most important discoveries in human history. And that is why the scientific response that followed, multiple teams finding that the same data was consistent with non-biological explanations, that the signal was statistically marginal, that DMS in a hydrogen-rich atmosphere is a very different thing from DMS in an oxygen-rich atmosphere, was not a failure or a scandal, but exactly what the scientific process is supposed to produce when a claim of this magnitude is made. The story of K2-18b's DMS signal is not a simple story of discovery and confirmation. It is a story of detection, challenge, and the slow, careful work of establishing what the evidence actually supports. It begins, technically, in 2023. Madhusudhan's team published their first JWST results using near-infrared instruments. The paper reported the detection of methane at high confidence, around 5 sigma, carbon dioxide at around 3 sigma, and a tentative, low-significance signal that was consistent with DMS. The paper was careful. The DMS signal was described as tentative and potential. The paper's headline conclusions emphasized the methane and carbon dioxide as the robust results. It is worth pausing to appreciate how significant the methane and carbon dioxide detections were on their own, independent of anything to do with DMS. For decades, astronomers had been able to study the atmospheres of large, hot gas giants, planets orbiting close to their stars, puffed up and easy to observe. But a temperate, habitable zone world was a far harder target. To detect specific carbon-bearing molecules in the atmosphere of a planet sitting in its star's habitable zone was a genuine first. A demonstration that the technology had finally reached the point where the atmospheres of potentially habitable worlds were within reach. Whatever happens with the DMS question, that achievement stands. It marked the moment when the study of habitable zone exoplanet atmospheres moved from aspiration to reality. Multiple teams independently analyzed the same data. Some independent reanalyses confirmed the methane detection strongly, but found weaker or no statistically significant evidence for carbon dioxide, using alternative data reduction pipelines. This discrepancy in the carbon dioxide detection highlighted how sensitive the results were to data reduction choices, a theme that would recur throughout the K2-18b story. Other groups published modeling work, arguing that K2-18b's atmospheric data was equally consistent with a gas-rich mini-Neptune model, a planet more like a small, gaseous ice giant than a Hycean ocean world. In that model, there is no habitable surface and no possibility of the marine biosphere that the DMS hypothesis invokes. Still others raised the possibility of a magma ocean world, about as inhospitable as it gets. The Hycean world interpretation, in other words, was not the only interpretation consistent with the data. It was one of several. In April 2025, Madhu Sudhan's team returned with new data. They had obtained observations using JWST MIRI instrument, extending the spectral range into the mid-infrared, roughly 5 to 12 microns. This wavelength range was specifically targeted because DMS and DMDS have absorption features there. The MIRI data showed features the team interpreted as consistent with DMS and or DMDS at around 3 sigma confidence. The paper was published. The Cambridge press release went out. The headlines arrived. Within days, the scientific scrutiny began. A researcher at the University of Oxford performed a rapid independent analysis using an agnostic retrieval approach, testing whether the spectral features specifically required DMS, or whether they could be explained by other molecules without assuming DMS in advance. The deliberately model-independent method found no statistically significant evidence specifically for DMS. A brief research note followed within days. The note mattered because it was the first independent check, and it suggested that the case for DMS was fragile in a specific way. It depended on the assumptions built into the retrieval model. When those assumptions were relaxed and the data was asked what it showed without prior expectation, DMS did not emerge robustly. More analyses followed. In July 2025, a NASA-led team led by Rin Yu, who at the Jet Propulsion Laboratory published a thorough reanalysis incorporating 4 new transit observations, more data than any previous K2-18b study, and crucially, involving Madhu Sudhan as well as other independent teams in a collaborative, multi-team approach. They robustly confirmed methane and carbon dioxide. They confirmed that K2-18b's interior is water-rich. They found only marginal evidence for DMS, and they conducted photochemical modeling of K2-18b's atmosphere, identifying pathways by which DMS and related organosulfur molecules could, in principle, be produced in a hydrogen-rich atmosphere through photochemical reactions, processes that simply do not occur in Earth's oxygen-rich atmosphere. The collaborative structure of this study deserves note, because it represents a healthy way for a contested question to be handled, rather than competing teams firing papers at each other across the literature. The WHO et al. Effort brought several groups, including Madhusudhan's own, together to analyze a common, expanded dataset, each developing its own interpretation within a shared framework. This is science working as it should. Not as a contest to be won, but as a collective effort to converge on what the data can actually support. That the team Madhusudhan participated in reached more cautious conclusions about DMS than his April paper had is not a contradiction or an embarrassment. It is the normal, healthy process by which an initial result gets tested against more data and more eyes. The thrust of the WHO team's conclusion was that atmospheric processes on K2-18b that do not involve life, particularly photochemistry, can also, in principle, produce organosulfur molecules, which means that DMS on its own may not be a definitive sign of life on this planet. A joint analysis combining all available JWST instruments, NIRIS, NIRSPEC, and MIRI, found insufficient evidence for DMS and DMDS. Other agnostic retrievals across the full dataset found that the data was consistent with non-biological molecules and did not require DMS to explain it. And a separate team searched the spectral data against a large library of candidate molecules, hundreds of them, rather than a preselected set. They found moderate evidence for many molecules, including DMS, but also including other organosulfur compounds and simple hydrocarbons, such as ethane. As one of those researchers put it, almost anything with a carbon bonded to 3 hydrogens shows up at that wavelength. Dimethyl sulfide does, but so do many other molecules, and even with better data, it will be hard to identify DMS uniquely. The implication was troubling. The spectral region where the DMS signal was claimed was not, with current data, discriminating enough to single out any one specific molecule. Later, in 2025, a summary paper appeared with a title that captured the community's assessment precisely. K2-18b does not meet the standards of evidence for life. It reviewed the available analyses, summarized what was robustly detected: methane, carbon dioxide, a water-rich interior, and what was not. A confirmed biosignature. Let us slow down and make the core concepts here concrete. Because the K2-18b story depends on understanding a few things precisely: what transmission spectroscopy can and cannot do, what DMS actually is as a biosignature, and what 3 sigma confidence means in the context of claiming alien life. Think of it this way. Imagine you are trying to detect a faint trace of a specific perfume in the air of an entire stadium, from a seat on the opposite side, using a sensitive instrument pointed at a single spotlight whose beam passes through the air above the field. The instrument measures which wavelengths of the spotlight's light are absorbed as it travels through the air. The perfume absorbs at specific wavelengths. If you can detect those absorption features clearly enough, above the noise of everything else in the air, you can infer that the perfume is there. That is, at a rough conceptual level, what JWST is doing with K2-18b's atmosphere from over 100 light-years away. The measurement precision required is staggering. The signal being sought is a tiny fraction of the star's total brightness. And the molecule being sought, DMS, is not the only molecule that absorbs at those wavelengths. The analogy can be pushed a little further to capture the heart of the difficulty. Suppose the perfume you are listening for shares many of its notes with other, far more common sense in the stadium air: the smell of food, of crowds, of cut grass. If your instrument is sensitive but not perfectly precise, a faint reading at the perfume's wavelengths might genuinely be the perfume, or it might be a combination of those more ordinary smells that happen to overlap at the same wavelengths. To be sure it is the perfume specifically, you would need either a much cleaner reading, or measurements at additional wavelengths where the perfume differs from everything else. This is exactly the situation with DMS on K2-18b. The feature is there, but the wavelengths where it appears are shared by other molecules, and the reading is not yet clean enough to say which one is responsible. That is not a flaw in the work. It is an honest reflection of how hard the measurement is at the very edge of what the instrument can do. There are three concepts you need to understand clearly. The first is what a biosignature actually is, and the specific challenge it presents. A biosignature is a chemical, physical, or structural feature whose presence in a planet's atmosphere or on its surface is best explained by biological activity. On Earth, oxygen is a biosignature. The free molecular oxygen in our atmosphere would react away on geological timescales without continuous replenishment from photosynthesis. DMS is considered a biosignature on Earth because no known non-biological process in an oxygen-rich atmosphere produces it in detectable quantities. The deep idea underneath the biosignature concept is chemical disequilibrium. Left alone, the chemistry of a planet's atmosphere will tend toward equilibrium, a stable state where reactions have run their course and nothing much changes. Life disrupts this. By constantly producing and consuming gases, living systems hold an atmosphere away from equilibrium, in a state that pure chemistry and geology, on their own, could not sustain. Earth's oxygen-rich atmosphere is a dramatic example. It is wildly out of chemical equilibrium, and it stays that way only because life continuously pumps oxygen into it. So, when astrobiologists look for biosignatures, they are really looking for signs of chemistry that should not persist without something actively maintaining it. A molecule that ought to be destroyed quickly, yet is present in abundance, implies a source replenishing it. And if no non-biological source can do the job, life becomes the leading explanation. The critical phrase in both cases is, on Earth. A biosignature is not a molecule that is always and everywhere a sign of life. It is a molecule that, in a specific atmospheric context, cannot be present at observed concentrations without life. The argument only transfers to another planet if that planet's atmospheric context is similar enough that the same chemistry applies. K2-18b's atmosphere is not similar to Earth's. It is hydrogen-rich, not oxygen-rich, and it appears that hydrogen-rich atmospheres may provide non-biological production pathways for DMS that do not exist in Earth's atmosphere. The second concept is what 3 sigma means. In science, sigma is a measure of statistical significance, roughly how unlikely it is that a result arose purely by chance. A 3 sigma result corresponds to a chance probability of roughly 1 in 370. That sounds impressive, and for much of science, 3 sigma is considered meaningful evidence worth reporting. But for a claim as extraordinary as signs of life on another planet, many researchers argue the standard should be far higher, closer to the 5 sigma standard used for particle physics discoveries, which corresponds to a chance probability of about 1 in 3. 5 million. 3 sigma, in this context, is interesting. It is not, by itself, a discovery. There is an old principle in science, often associated with Carl Sagan, that extraordinary claims require extraordinary evidence. The discovery of life beyond Earth would be perhaps the most extraordinary claim in the history of the field. It is the kind of result that would be taught in every textbook, that would reshape how our species understands itself, that would never be forgotten. A claim of that magnitude cannot rest on evidence that, by the standards of much less consequential discoveries, would already be considered borderline. This is not about doubting the competence of the researchers involved. It is about matching the strength of the evidence to the weight of the conclusion. A 1 in 370 chance of a statistical fluke might be perfectly acceptable for, say, characterizing the atmosphere of a hot gas giant where nothing momentous hangs on the result. For announcing that we are not alone in the universe, it is nowhere near enough. The history of science contains a number of cautionary tales, claims announced at modest significance that evaporated under scrutiny, and the biosignature field is acutely aware that it cannot afford a high-profile false positive. The third concept is the molecular attribution problem. Even if a signal at DMS wavelengths is real, not noise, genuinely present in the spectrum, it may not be DMS specifically. The mid-infrared spectral region where the feature appears is crowded. Multiple molecules absorb at overlapping wavelengths there: ethane, various sulfur compounds, and many others. To claim the feature is specifically DMS requires showing that DMS fits the data significantly better than all other candidate molecules. The large library analysis, testing hundreds of molecules, showed that many of them fit the K2-18b spectrum at comparable statistical significance. This does not rule out DMS, but it undermines the claim that DMS is the uniquely preferred interpretation. One of the researchers involved in that analysis put the problem memorably. Almost anything with a carbon atom bonded to 3 hydrogen atoms will absorb at roughly these wavelengths. That structural motif, a carbon bonded to 3 hydrogens, a methyl group, is extremely common in organic chemistry. It appears in DMS. It also appears in ethane, in many other organosulfur compounds, and in a long list of simple organic molecules. So, a feature at these wavelengths tells you, fairly reliably, that something with that common structural motif is present. It does not tell you which something. Distinguishing DMS from its many cousins requires either much higher quality data, or measurements at additional wavelengths where the molecules' barcodes diverge. With the data currently in hand, that distinction cannot be made cleanly, which is why the same spectrum can support a confident-sounding DMS retrieval and an equally valid retrieval favoring ethane or another molecule entirely. Here is where the stakes start to rise in a way that is simultaneously personal and civilizational. If DMS were present at the levels the Madhusudhan team's analysis suggested, and if it were genuinely of biological origin, then K2-18b would host life. Not just the possibility of life, not just the precursors of life. Life productive enough to generate DMS at levels far above Earth's, in the ocean of a world that orbits a dim red star over 100 light-years from here. The implications would be staggering, not just for astronomy, for philosophy, for religion, for everything humans have thought and believed and feared and hoped about our place in the universe. If there were life on K2-18b, then life is not a cosmic accident confined to a single lonely planet. It is something the universe does, given the right conditions, perhaps often. The Fermi paradox would take on new dimensions. The Drake equation would get empirical constraints. Many of our assumptions about what is ordinary and what is exceptional in the cosmos would have to be revised. It is worth being concrete about why a single confirmed example would matter so enormously. Right now, in everything we know, life has emerged exactly once, on exactly one planet, our own. From a sample size of 1, we cannot tell whether life is a near-miraculous fluke, something so improbable that we might be alone in the observable universe, or whether it is a near-inevitable consequence of the right chemistry and the right conditions, something that springs up wherever it can. These two possibilities could hardly be more different in their implications, and a sample of one cannot distinguish between them. A single second example, life found independently on another world, would change that instantly. It would tell us that life is not unique to Earth, that the process which produced us has happened at least twice, and therefore, almost certainly, many times across a universe of hundreds of billions of galaxies. That is why even a marginal hint of a biosignature commands the attention it does. It is not the molecule itself that matters. It is what the molecule, if confirmed, would tell us about whether we are alone. The scientific community understood these stakes perfectly well in April 2025, which is precisely why the multiple independent reanalyses appeared so quickly and why the scrutiny was so intense. This is not a claim that can be allowed to stand if the evidence does not support it. The damage of a false discovery, to public trust in science, to the credibility of astrobiology as a field, to the careers of everyone involved, would be severe, and the potential significance of a genuine discovery demands the highest possible standard of evidence before the claim is endorsed. The 3 sigma DMS signal at K2-18b is the first JWST result that forced this specific tension between genuine excitement and the requirement for genuine proof into the open in a public and consequential way. Whatever its final resolution, that tension may be the most important thing K2-18b has produced. The DMS debate is, in one sense, a debate about a specific signal in a specific spectrum of a specific planet. But underneath that specific debate is a deeper question that the K2-18b story has forced into the open. What does biosignature confirmation actually require? Not, what does biosignature detection require? Detection is what happened at K2-18b, a signal that might be a biosignature. Confirmation is something else. Confirmation means demonstrating, to a standard of evidence the scientific community accepts, that the signal requires biological activity to explain it, and cannot be the product of abiotic chemistry. That standard had never been fully tested against real data before K2-18b forced the issue. It is being defined now, and the process of defining it, the specific debates about thresholds, methodology, molecular attribution, and atmospheric modeling, is changing the search for life in ways that will matter long after the K2-18b DMS question is settled. The entire DMS as biosignature argument rests on a specific picture of K2-18b. In that picture, K2-18b is a Hycean world. Under a thick hydrogen atmosphere, the planet has a liquid water ocean at moderate temperature and pressure. In that ocean, life has evolved, specifically, life analogous to Earth's marine phytoplankton, the organisms responsible for most of Earth's DMS production. Those organisms are present in sufficient abundance to drive DMS into the atmosphere at high concentrations. This picture is internally consistent and scientifically motivated. The Hycean concept is based on real physics. Madhu Sudhin's 2021 paper introducing it was peer-reviewed and broadly accepted as identifying a plausible class of potentially habitable exoplanet. The problem is that this picture is one of several consistent with what we know about K2-18b. The planet's mass and radius tell us something important but ambiguous about its interior. An 8.6 Earth mass planet with a radius around 2.6 times Earth's is consistent with multiple compositions. It could be a rocky world with a thick hydrogen atmosphere and a liquid ocean, the Hycean model. It could be an ice-rich sub-Neptune, more like a small Uranus or Neptune in internal structure. It could be a gas-dominated mini-Neptune with a deep hydrogen envelope and no meaningful liquid surface. Some analyses have even raised the possibility of a hot magma ocean interior. The mass and radius data alone do not distinguish between these possibilities. The reason for this ambiguity is fundamental, and it affects every planet in this size range. Mass and radius together give you a planet's average density, but many different internal structures can produce the same average density. A given mass and radius could describe a relatively small rocky core wrapped in a deep, light hydrogen envelope, or a larger, denser interior of water and ice with a thinner atmosphere. These are physically very different worlds, with very different prospects for habitability. Yet from the outside, they can look nearly identical in the only two bulk properties we can measure directly. This is sometimes called the degeneracy problem for sub-Neptunes, and it is one of the central difficulties in the study of this class of planet. K2-18b sits squarely in the size range where the degeneracy is worst. Without additional information, and the atmosphere is the main additional information available, we genuinely cannot say from mass and radius alone what kind of world it is. Independent modeling work has shown that K2-18b's atmospheric observations are consistent with the gas-rich Mini-Neptune model, as well as the Hycean model. In the Mini-Neptune case, the planet has no habitable surface, and the DMS-producing marine biosphere of the Hycean picture does not exist. The NASA-led Hu et al. Work in July 2025 added important information. Using new transit data and careful modeling, the team concluded that K2-18b does have a water-rich interior. The planet is not a dry world, something wet is there. But whether that wet interior is a surface ocean at habitable conditions, or a deep, high-pressure, high-temperature water layer at conditions incompatible with life as we know it, could not be determined from the atmospheric data alone. Some interpretations of the planet's likely temperatures suggest the relevant water layer could be far too hot for life. This pattern, evidence consistent with multiple models, each piece ambiguous on its own, defines the current state of K2-18b science. For DMS to be a biosignature at K2-18b, you would need, in sequence, a Hycean world rather than a Mini-Neptune or magma world, a genuinely habitable ocean life in that ocean life. The third is the retrieval methodology. An atmospheric retrieval is a statistical method that infers the most likely atmospheric composition from a measured spectrum. It requires specifying which molecules to test for. If you specify DMS in advance, motivated by the Hycean hypothesis, you test whether DMS is present and report the significance of the evidence for it. If you use an agnostic method that does not specify molecules in advance, you ask which molecules the data supports without prior assumptions. In K2-18b's case, the targeted DMS retrieval found around 3 sigma evidence. Agnostic retrievals found no significant evidence specifically for DMS. This is not a contradiction. It reflects the fact that the targeted approach was optimized to look for DMS, while the agnostic approach was not. But it means the 3 sigma result depends critically on the choice to look specifically for DMS. The fourth, and most troubling, is the molecular library size. When researchers searched K2-18b's spectrum against a large library of candidate molecules, they found moderate evidence for many of them, not just DMS, but other organosulfur compounds and simple hydrocarbons like ethane. When any molecule that absorbs in the relevant spectral region is tested, many of them produce evidence comparable to DMS in the current data. This does not mean DMS is absent. It means the current data cannot uniquely identify DMS over its competitors. That is the molecular attribution problem in its sharpest form, and it is the specific technical challenge that future observations need to address. There is also the abiotic production question. The WHO team's photochemical modeling showed that organosulfur molecules, including DMS, can in principle be produced in hydrogen-rich atmospheres by photochemical reactions that do not occur in oxygen-rich atmospheres. The rate of such abiotic production depends on parameters of K2-18b's atmosphere that are not currently well constrained. And some researchers have noted that the specific conditions required for efficient abiotic DMS production, such as a large reservoir of hydrogen sulfide, are not clearly present in the data. The key point is more modest but important. DMS, in K2-18b's atmospheric context, is not the unambiguous biosignature it would be on Earth. The assumption that DMS requires life, true on Earth, does not automatically transfer to a hydrogen-rich atmosphere around a red dwarf. This does not mean DMS is definitely abiotic on K2-18b. It means the biological interpretation is not the only one available. The K2-18b controversy has forced the exoplanet community to confront, in practical terms, what biosignature confirmation actually requires. Several requirements have come into focus. The first is statistical significance meeting a discovery standard. 3 sigma is meaningful evidence for most purposes, but for the most extraordinary claim in science, many researchers argue it is insufficient, that something closer to the 5 sigma particle physics standard is appropriate. The counter-argument, made by Matthew Sudhin's team, is that 5 sigma may be unreachable with current instruments on reasonable timescales, and that science should report what it finds with appropriate caveats. That argument is defensible, but it means the April 2025 result should have been presented and covered as preliminary evidence requiring extraordinary scrutiny, not as a near discovery of life. The second is molecular attribution at sufficient specificity. Finding a feature consistent with DMS is not the same as detecting DMS. Detection requires showing DMS is the preferred explanation over all other candidates. The large library result shows this requirement has not been met. Better data, particularly higher spectral resolution in the relevant range, is needed. The third is abiotic exclusion. A biosignature claim requires showing not just that a molecule is present, but that its presence requires life and cannot be explained by abiotic chemistry in that planet's specific context. On Earth, DMS satisfies this. On K2-18b, the existence of plausible abiotic photochemical pathways means this requirement has not been met. The fourth is contextual plausibility. Even if DMS were present and could not be explained abiotically, the concentrations would need to be consistent with a plausible biosphere. Energy budget analyses suggest that producing DMS at the high levels implied would require biological production rates that are difficult to achieve given the energy available to a K2-18b ocean biosphere. The fifth, and deepest, is the ensemble standard. The growing consensus is that no single molecule should be treated as a definitive biosignature. The strongest case uses an ensemble, a combination of molecules whose simultaneous presence is so unlikely through abiotic processes that biology becomes the overwhelmingly favored explanation. On Earth, the simultaneous presence of oxygen, methane, and related gases in observed ratios cannot be maintained without life. For Hycean worlds, the equivalent ensemble has not yet been defined. Defining it is now one of the most important open problems in the field. The logic of the ensemble approach is worth making explicit because it is genuinely clever. Consider Earth's atmosphere. It contains abundant oxygen, and it also contains methane. These two gases react with each other. In the presence of sunlight, they should chemically destroy one another over relatively short timescales. The fact that both are present together in substantial quantities, means something must be continuously replenishing them, both on Earth, that something is life. Photosynthesis pumping out oxygen, and biological processes generating methane, faster than the two can react away. No known, non-biological process can sustain this particular chemical disequilibrium at the observed levels. So, it is not the oxygen alone, or the methane alone, that makes the case. It is the two of them coexisting in a way that abiotic chemistry cannot explain. The ensemble is the signature, not any single molecule. The challenge for Hycean worlds is that nobody has yet worked out which combination of molecules, in a hydrogen-rich atmosphere, would play the role that the oxygen-methane pair plays for Earth. Until that combination is defined, even a confident detection of a single molecule like DMS cannot carry the full weight of a biosignature claim. K2-18b has made this problem concrete. Before April 2025, the ensemble question for Hycean worlds was theoretical. After it, it is a central methodological challenge. There are three ways to think about what the K2-18b story means for the search for life. They sit on a ladder, from most conservative to most bold. Each is held by researchers engaged seriously with this data. Each has supporting evidence, and the choice between them will be made, not by debate, but by the next generation of observations and modeling. The conservative interpretation is that the DMS signal is most likely abiotic, or not robustly present. K2-18b may not be a Hycean world, and the April 2025 announcement was premature. In this view, the signal is marginal and contested, and most plausibly explained either by competing molecules or by abiotic chemistry. The methane and carbon dioxide are real and interesting. The biosignature claim is not supported. The supporting evidence, the abiotic pathway modeling, the insufficient evidence reanalyzes, the large molecule library result, and the summary paper concluding the standards of evidence for life are not met. The weakness. The data does not definitively support this conclusion either. The signal may strengthen with better data, and the interior is genuinely water-rich. The moderate interpretation is that the DMS signal is intriguing, but ambiguous, and K2-18b remains among the best current targets for biosignature science, pending more observations. In this view, the methane and carbon dioxide detections are solid, the water-rich interior is solid, and the DMS feature deserves further investigation rather than dismissal. More JWST observations, specifically in the most diagnostic wavelength ranges, may strengthen or dissolve the signal. The supporting evidence. The recurrence of DMS-compatible features across observational epochs, the confirmed water-rich interior, and the legitimate theoretical prediction that Hycean worlds could produce detectable DMS. The weakness. More data may not resolve the attribution problem if JWST spectral resolution in this range is simply insufficient to single out DMS. The bold interpretation is that K2-18b may be the first exoplanet with a detectable biosphere, and the evidence will strengthen with future observations. In this view, the DMS/DMDS signal is real and biological. The Hycean model is correct, and the analyses finding insufficient evidence will eventually be shown to have been too conservative. The supporting evidence. The persistence of DMS-compatible features, and the theoretical case for DMS detectability in Hycean worlds. The weakness. This view requires setting aside the abiotic pathway modeling, the large library attribution problem, and the multiple independent retrievals that found no robust DMS, while accepting a chain of unverified assumptions about the planet's surface, ocean, and biosphere. Here is what needs to be said before we leave the interpretive landscape. The K2-18b story is not, at its core, about whether one team was right or wrong. It is about how the search for life beyond Earth actually works in practice. Before April 2025, biosignature science was largely theoretical and aspirational. Researchers had spent decades developing frameworks for what biosignatures would look like, building the telescopes that might detect them, and writing papers speculating about what a detection would mean. But they had never actually had a candidate biosignature signal, in real data, that forced them to answer the question in practice: is this life? K2-18b provided that signal. It was not confirmed as biological, but the process of analyzing it, contesting it, modeling the alternatives, and developing the methodology to distinguish the interpretations has produced a more rigorous, more honest, and more capable biosignature science than the field possessed before. The K2-18b story is not the discovery of life. It is, in a sense, the discovery of what life's discovery would actually require. After everything we have seen, the April 2025 announcement, the multiple independent analyses, the abiotic pathway modeling, the 3 interpretations, the summary paper. The question is no longer whether JWST found something important at K2-18b. It did. The question is what that discovery means for the future of the search, and here is where the story takes a turn that most coverage has never gotten to. Remember what we asked at the start. What exactly did JWST find on K2-18b? Why was the April 2025 announcement met with both excitement and significant skepticism? And what does the debate around the DMS signal tell us about where biosignature science actually stands? Here is what we now know, and, just as importantly, what we still do not. We know K2-18b has methane and carbon dioxide in its atmosphere, confirmed robustly by multiple independent teams. This is among the first detections of carbon-based molecules in a habitable zone exoplanet atmosphere in the history of astronomy. We know K2-18b has a water-rich interior, inferred from the 2025 atmospheric modeling. The planet is wet. We know the DMS signal sits at around 3 sigma in the 2025 MIRI data, and that it is marginal, contested, and cannot currently be uniquely attributed to DMS over competing molecules. We know that abiotic photochemical production of DMS is, at least in principle, possible in a hydrogen-rich atmosphere. We do not know whether K2-18b is a Hycean world or a gas-rich sub-Neptune. We do not know whether life is present, and we do not know what the DMS-compatible spectral feature actually is. That is where the science currently sits. Here is the strange thing about how K2-18b has been covered in popular media. The coverage exists in 2 phases. The first, the April 2025 announcement, produced some of the most extensive science news coverage since the first JWST images. Every major outlet. Headlines implying we had found, or nearly found, life beyond Earth. The second phase, the independent reanalyses, the abiotic pathway modeling, the summary paper, produced far less coverage, reaching a much smaller audience. The gap between the two, in public awareness, is enormous. Let me tell you specifically what the popular coverage missed. The first is the 3 sigma issue. Most popular articles did not explain what 3 sigma means or how it relates to a discovery standard. A reader who saw the headlines without the statistical context would conclude that scientists had found DMS on K2-18b. A reader with the context would understand that scientists had found a signal that might be DMS, with a chance probability of roughly 1 in 370. In data near the limit of what JWST can currently achieve. Those are very different messages. There is a structural problem underneath this, and it is not unique to K2-18b. The incentives of science communication push relentlessly toward the dramatic version of any story. A headline that says a possible signs of life detected will be read and shared far more widely than one that says marginal spectral feature consistent with several molecules, including one associated with life on Earth, detected at modest statistical significance. The second headline is more accurate, the first is more compelling, and in the gap between them, public understanding gets distorted, not usually through any single false statement, but through emphasis, omission, and the natural human appetite for a thrilling story. The K2-18b episode is a near-perfect case study in this dynamic, because the science itself was done carefully and hedged appropriately, and the distortion happened almost entirely in the translation from careful paper to confident headline. The second is the abiotic pathway. The finding that photochemistry in a hydrogen-rich atmosphere can in principle produce DMS without life received modest specialist coverage, but did not reach the audience the April announcement did. Most people who saw the original headlines remain unaware that a plausible non-biological explanation exists. The third is the large library analysis. The finding that many non-DMS molecules, including ethane, fit the spectrum at comparable significance, is the single most important context for understanding why the claim is contested. It was largely absent from popular coverage. The fourth is what confirmation would actually require. Almost no popular article explained what additional observations would be needed to move from a marginal detection to a confirmed biosignature. How many more transits? What spectral resolution? What laboratory measurements? What modeling? Without this, readers had no framework for judging whether the question would be resolved quickly or might remain open for years. The fifth, and most important, is the methodological significance of the controversy itself. The K2-18b story is not primarily about whether DMS is present on one planet. It is about the state of biosignature science, what the field can and cannot currently do, and about how this controversy has driven rapid development of the methodology the field needs. That story, the improvement of the methodology, may matter more for the long-term search than the DMS signal itself, and it was almost entirely absent from popular coverage. In the months since the summary paper, work on K2-18b and on biosignature methodology has continued. The first development is continued JWST observations. The Madhu-Sudhin team has continued accumulating transits with two goals: to improve the signal-to-noise on the DMS-compatible feature, to see whether it strengthens or dissolves with more data, and to extend coverage in the wavelength ranges most diagnostic for distinguishing DMS from competitors. As of 2026, the community awaits an updated analysis of the accumulating dataset. Independent teams are also continuing to analyze available data, and comparisons with other sub-Neptunes are proving valuable. Another habitable-zone sub-Neptune that JWST has observed extensively shows methane and carbon dioxide, but no comparable DMS signal. Comparing the detailed atmospheric chemistry of two broadly similar planets helps identify which spectral features are specific to K2-18b and which are common to the class. This comparative approach is one of the most powerful tools available, and it is worth understanding why. A single planet, studied in isolation, offers no baseline. If you see an unusual feature, you have nothing to compare it against. You cannot easily tell whether it is genuinely special or simply the kind of thing this class of planet does. But once you have several planets of similar size, temperature, and atmospheric type, you can begin to build a picture of what is normal for the class and what stands out. If K2-18b shows a feature that broadly similar planets do not. That makes the feature more interesting and more likely to be telling us something specific about K2-18b. If, on the other hand, the feature turns out to be common across the class, that points towards some ordinary process, chemistry or physics shared by all such planets, rather than anything as exceptional as life. As JWST observes more sub-Neptunes in the habitable zone, this kind of population-level comparison will become an increasingly important check on claims about any individual world. The study of exoplanet atmospheres is gradually shifting from the examination of single objects to the comparison of populations, and that shift will make every future biosignature claim easier to evaluate in context. The second development is in laboratory measurements. One specific gap the controversy exposed was the quality of laboratory data on DMS and related molecules at the temperatures and pressures relevant to K2-18b. If the cross-sections used in retrieval models are inaccurate, the retrieval will be inaccurate even with perfect spectra. Laboratory groups have accelerated programs to improve these measurements, which will improve the reliability of attribution in current and future data. The third development is the case for the next generation of telescopes. The K2-18b debate has sharpened the argument for the Habitable Worlds Observatory, a planned next-generation space telescope designed for biosignature detection, focused on Earth-like planets around Sun-like stars, observed by direct imaging rather than transit spectroscopy. The biosignature science for that class of target, oxygen-rich atmospheres, where DMS would more clearly require biological production around stable stars, is considerably cleaner than for Hycean worlds around red dwarfs. The K2-18b controversy has not undermined that concept. It has strengthened the case for it. The distinction between transit spectroscopy and direct imaging is worth understanding, because it points toward where the field is heading. Transit spectroscopy, the method used for K2-18b, only works when a planet happens to pass between us and its star, and it measures starlight filtered through a thin ring of atmosphere. It is powerful but indirect, and it works best for large planets tightly orbiting small stars, which is why red dwarf systems like K2-18 are favorable targets. Direct imaging is different. It aims to block out the overwhelming light of the star and capture the faint light of the planet itself, separated from its star. This is far more technically demanding. It has been compared to spotting a firefly next to a searchlight from across a continent, but it would allow astronomers to study Earth-like planets around Sun-like stars, in oxygen-rich conditions where the biosignature logic is cleaner and better understood. The Habitable Worlds Observatory is conceived to do exactly this. The lesson of K2-18b is not that the search is hopeless. It is that the cleanest path to a confident answer may run through a different kind of target and a different kind of instrument than the ones that produced the first tantalizing hint. The fourth development is the ensemble biosignature framework for Hycean worlds. Multiple groups are now working explicitly on what combination of molecules would constitute a robust, non-abiotically explainable biosignature in a hydrogen-rich atmosphere. The emerging consensus is that a single molecule, even DMS, even at high confidence, is insufficient. The case for life would need DMS or another organosulfur compound at high confidence and uniquely attributed. Atmospheric chemistry, inconsistent with abiotic models across a range of assumptions. And ideally, at least one additional independent biosignature whose simultaneous presence cannot be explained without biology. Defining this standard for Hycean worlds is work the K2-18b controversy has made urgent, and here is what makes the K2-18b story truly remarkable. Not the signal, not the announcement, Not the controversy. What makes it remarkable is this. Before April 2025, biosignature science existed almost entirely in the space of hypothesis and prediction. Researchers had defined what biosignatures would look like, built telescopes to detect them, written frameworks for what a detection would mean, but they had never actually had to answer the question against real data. K2-18b gave them the question, a real signal, in real data, from a real planet. A molecule that, on Earth, is made by marine life. Is this life? The answer the scientific community gave was the most valuable answer it could have given. Not yes, not no, not we don't know. The answer was, here is specifically what we do not know, here is specifically why we cannot yet tell, and here is specifically what we would need in order to tell. That answer is more valuable than a premature yes would have been, and more valuable than a premature no, because it is an honest, specific, actionable characterization of the gap between where the field is and where it needs to be. There is a particular kind of scientific maturity in being able to say, precisely, what you do not know. A field in its infancy can only say, we don't know, in a vague, hand-waving way. A mature field can map its own ignorance in detail, can point to the specific measurement that is missing, the specific model that needs refining, the specific standard that needs defining. The response to K2-18b demonstrated that biosignature science has reached that second stage. The community did not simply throw up its hands. It produced a detailed, itemized account of exactly what stands between the current evidence and a confident answer. That itemized account is, in a real sense, a roadmap. It tells the field what to build next. Let that sit for a moment. Perhaps the most important thing JWST found at K2-18b was not dimethyl sulfide. It was the specific shape of our own ignorance. The places where the atmospheric models are insufficient, the molecular cross-sections that need better measurement, the spectral resolution needed to distinguish DMS from competitors, the abiotic pathways that need to be characterized, the ensemble standard that needs to be defined. All of these existed before April 2025 as theoretical limitations discussed in workshops and telescope proposals. But they were not urgent. K2-18b made them urgent, concrete, and actively addressed. The announcement, and the controversy that followed, accelerated the development of biosignature science by years. We have never been closer to being able to detect life beyond Earth than we are now. The instruments exist, the techniques exist, the candidate targets exist. What does not yet exist, in fully developed form, is the methodology rigorous enough to confirm a detection if one is made. That methodology is being built, and it is being built because K2-18b forced the question. We may be one generation from the answer, maybe less, but there is one more piece to this story. Because K2-18b is not the only exoplanet where JWST has been finding unexpected atmospheric chemistry. There is another world, smaller, in a different situation, where JWST has found chemistry that does not fit standard expectations, and where the most likely explanation seems to involve the planet's interior being more active and more complex than models predicted. It is not a biosignature. It is something different. A reminder that exoplanet atmospheres are more surprising than we expected, and that the surprises are not confined to habitable zone worlds around red dwarfs. That is a story for next time. Tonight, we did not just learn about molecules on a distant exoplanet. We watched what happens when the most powerful space telescope ever built points at one of the most promising candidates for life beyond Earth. And what it finds is simultaneously thrilling and insufficient. We saw Niku Madhusudhan in Cambridge, opening the MIRI data and finding the mid-infrared feature, his models had flagged as consistent with DMS, a molecule produced on Earth overwhelmingly by marine life. We saw a press release describe it as the strongest sign yet of a possible biosignature. We saw the world respond with the excitement that the possibility deserves, and we saw the scientific community do what it is supposed to do. Multiple independent teams analyzing the same data with different methods. A NASA-led team identifying an abiotic photochemical pathway. A team searching hundreds of molecules and finding that many fit the spectrum at comparable significance. A summary paper stating plainly that the standards of evidence for life had not been met. It is worth appreciating how fast all of this happened. The original paper appeared in April. Within days, the first independent reanalysis was public. Within months, several major studies had re-examined the data, new photochemical models had been built, and a community framework paper had assessed the claim against formal standards of evidence. This is the immune system of science working at full speed. A high-profile claim provoking, almost immediately, a coordinated, rigorous, and largely collegial effort to test it from every angle. Far from being a sign of dysfunction, it is exactly what you would want to see. The system that is supposed to catch premature claims caught this one quickly, and in the process built tools that will serve every future claim. The headline said we found life. The science said we found a signal that might be consistent with life, that is also consistent with non-life, and that requires better data, better models, and better methodology before it can be called a biosignature in the scientific sense. Both things are true, and the distance between them, between what the headline said and what the science showed, is where some of the most important work in astronomy is currently being done. The answer is not here yet, but the methodology being built to reach it, the frameworks, the standards, the laboratory programs, the telescope proposals, that is here. And it is here because K2-18b forced the question. Even now, the K2-18b picture is not resolved. The methane and carbon dioxide are confirmed. The water-rich interior is inferred. The DMS signal is contested, marginal, and cannot be uniquely attributed to that specific molecule with current data. Whether additional JWST observations will strengthen the signal toward a discovery threshold or reveal it as noise is not yet known. The Madhu-Sudhin team is accumulating more transits. The community awaits the next analysis. Whether K2-18b is a Hycean world with a surface ocean remains unknown. Whether the abiotic DMS production rate in its specific conditions is sufficient to account for the feature, or whether biology would be needed, requires better photochemical models that are under development, and the ensemble biosignature standard for Hycean worlds is being developed but is not yet fully defined. All of these questions are being actively worked on. The answers will come from data. There are a few things worth taking from this story that go beyond K2-18b. The first is that finding a molecule associated with life is not the same as finding life. The gap between consistent with biology and requires biology is the central methodological challenge of biosignature science. K2-18b has made that gap concrete in a way no theoretical discussion could. The second is that statistical significance matters, and the vocabulary of evidence matters. 3 sigma is not a discovery. The failure of popular coverage to convey this is a genuine science communication failure that K2-18b has brought into sharp focus. The third is that context is everything. DMS is a biosignature on Earth because Earth's atmosphere is oxygen-rich and no abiotic pathway exists there. K2-18b's hydrogen-rich atmosphere may provide a pathway Earth does not have. A molecule that is a biosignature in one atmospheric context may not be one in another. This is perhaps the single most transferable lesson of the entire episode. The search for life cannot rely on simple chemical checklists imported from Earth. It has to be grounded in a deep understanding of each target planet's specific chemistry, because the same molecule can mean entirely different things in different worlds. The fourth is that controversy drives progress. The rapid development of biosignature methodology that followed the announcement happened because a real claim forced a real response. Science advances fastest when its claims are tested most rigorously. The reanalyses, the photochemical modeling, the framework papers, none of that would have happened with the same urgency without a concrete claim to test. In that sense, the value of the April announcement does not depend on whether its central claim survives. The claim served its scientific purpose simply by being specific enough and important enough to provoke the response it did. And the fifth is this: we are closer to being able to answer one of the most important questions in science than at any previous point in human history. The tools exist, the targets are known, the methodology is being built, and the question, once considered almost purely philosophical, is becoming empirically approachable within a human generation. That is what K2-18b showed us, not life, the proximity to the answer. So, I want to leave you with a few questions tonight. What would it actually take to convince you that a distant exoplanet hosts life, a single molecule, a combination of molecules, a signal that no abiotic explanation could account for? And what should it take to convince the scientific community? What standard of evidence should we require before announcing one of the most important discoveries in human history? When the April 2025 announcement went out and the world responded with excitement, was that response appropriate? Was the scientific skepticism that followed a failure of nerve? Or was it the field protecting the integrity of a process that matters enormously? And what does it say about us, about what we want, that the most honest thing the scientific community could say about the most talked about biosignature signal ever detected was, "Not yet, not enough, come back when the evidence is stronger"? Is that patience, or is it science? Sit with that. It may be the same question. If this story stayed with you, tell me in the comments, which moment was the one that pulled you in? Was it the April 2025 announcement and the genuine excitement it produced, the rapid reanalyses that complicated the picture, the abiotic DMS pathway that reframed the whole question, or the realization that what JWST found at K2-18b may be less important than what it revealed about the specific shape of what we do not yet know? I want to know. And if you want more stories like this, the search for life beyond Earth, told honestly, without the hype and without the dismissal, subscribe to Galaxy Pulse. We go beyond the headlines, every single time. I will see you in the next one. About 124 light-years away, a planet passes in front of its star. A fraction of the starlight passes through its atmosphere. A telescope in space measures the spectrum, and somewhere in that spectrum, at the very edge of what can currently be resolved, there may be a molecule that life makes, or there may not. We do not yet know, but we have never been closer to knowing, and that, in itself, is remarkable.